very similar to the one that we just did on the board number 35. Okay? So we are not going to be talking specifically about 4.4.
Would it be helpful to read that, though?
It might be helpful to sort of to take a look at it and read it. We're not going to, again,
Right.
go through the specifics of it, but
we're going to sketch curves and things, though, right?
yes. So the curve sketching that we've done up until now, section 4.4 basically summarizes everything that we've done. So yeah, I think it's a really good idea to read that section. We just won't lecture on it.
Okay.
Okay. So what we are going to talk about today is section 4.5, optimization problems. And this section is a section where we're going to be applying a lot of that information that we've been talking about first derivatives, about second derivatives, and what those tell us about the original function, and how that goes along with possibly real-life type questions. So here's our first example. We want to build a dog kennel. And we're going to attach it to our house. All right, so I adopted a dog, not this past summer, but the summer before. Her name is Maggie, and so I'd like to build a kennel for her on the side of my house, so that she can run around outside, away from the neighbor dog who she's scared to death of, and she will bark at. So I want to build this kennel on the opposite side of my house, and so I looked into my garage, and I noticed that I had some fencing left over from a previous project, and I have 60 feet of fencing. And I love my dog, so I want to make sure that the kennel that I create for her is as large as possible. So 60 feet of fencing, and we want the kennel with the biggest area possible for Maggie. Our job is to find the dimensions of the fence. The dimensions that we need for the largest area possible. Okay, so there's a lot of words up here in our property.
Are you asking for like a square, rectangle, like?
So that's a good question. Can I create a semicircular type kennel? And so maybe we should be a little bit more precise about this. We want a rectangular kennel, okay, which could encompass square. I mean, squares are also rectangles. So, but a rectangular kennel, no triangular pieces or any semicircles or anything like that. Okay, good question. All right, so just sort of imagining what's happening. Here I've got my house over here on the left side. And so I'm going to build a kennel that is rectangular, and then I'm going to stick Maggie inside the kennel. And she's going to be very happy. Okay. So the question that we might start to analyze is, well, if I kind of just sort of start to plan some things with this, some options for this kennel. Well, one thing I could do is I could be a little bit silly, and I could make this kennel very long. And here's my house still over here on the left side. And I have 60 feet of fencing, so I could make the kennel 2 feet wide, and then I'd have 58 feet left, and so that would mean that I would have, I think, 29 feet on each side of the kennel. And so if I do something like that, the first thing is that Maggie is now going to have to be stretched out very long, and she won't get to walk very, very far up and down. But I've got this kennel, and the area of this kennel, well, that's going to be 2 times 29, which is 58 square feet. Okay? So that would be a kennel that would be 58 square feet. Another extreme option that I could look at is I could create a kennel that is very wide in the opposite direction, so flat up against my house, and I could make the kennel, well, 1 foot's a little ridiculous, but maybe 2 feet away from the house. So I need 2 feet down here, and I need 2 feet up above here, and that's going to leave me with 56 feet left for that one side. And so the area for this kennel is going to be 2 feet times 56 feet. And so the area of that one is 112 square feet. Well, that's a little bit better than the prior choice. Okay? So I love my dog a little bit more if I create a kennel that looks like this. But the real question is, what type of dimensions do we need in order to make this rectangular area as large as possible? So what we might do is we might start to label some things on our picture up here. Okay? For example, I might label the top and the bottom side as X. Those two are always the same value. And then this other side, the side that's parallel to the house, I might give it a different label of Y. Now, I suppose that I could be a little bit more realistic about my kennel that I'm going to create. And so another option might be to take the 60 feet and put 20 feet on each side so that I create a full square. And so in that case, my area is 20 feet by 20 feet, which is 400 square feet. Okay, and that's way better than our first option and quite a bit better than our second option as well. Okay? So that seems like a much better option. The question is this the best choice? Will this make Maggie as happy as possible? Okay. Is that our largest area we can possibly have? Okay, so to answer this question of what should our dimensions be, what I want to do is I want to go back to my original question. We want to build a dog kennel attached to the house. We have 60 feet of fencing and one rectangular kennel with the biggest area possible. So I want to identify what it is that I'm trying to maximize, what it is that I'm trying to make as large as possible. In this case, that's area. Okay. So I'd like to come up with a formula for area. So in terms of our picture that we have here, if I want to calculate the area of this rectangle, what do I need to do? What's my formula here?
X times Y.
Yeah, x times y, so length times width for the area of a rectangle. So area is equal to x times y. And so what I've just written down there is a formula that describes area in terms of two input variables over here. Now, in Calc 1, we're talking about calculus of a single variable, and I don't want to have to deal with two variables over on this right side, so what I need is at least one more relation that I can write down to connect x and y. So since I have two variables, I want to find a relation connecting x and y that is different or independent from our formula a equals x times y. So I look back over here at the picture, and is there anything else in here that we can make a connection with that connects x and y in a way other than area is equal to x times y?
60 feet.
Okay, so yeah, this 60 feet, we know. So I went to my garage and I found that 60 feet of fencing. And so, well, what do you want to do with that 60 feet?
Subtract 2x from it.
Okay, so in terms of, we need that 60 feet to create the outside of our kennel. So we can figure out this y value if we take away the two x values. So one way that I might write this is I might say that 60 feet of fencing is equal to 2x plus y. So I'm using 2x sides plus 1 y side to give me my 60 feet. Okay, any questions about that relation? Okay. So now I'm going to use that relation to get rid of one of my variables up here. And so what I'll do is I'll do what Will suggested, and he says, okay, we're going to subtract 2x from 60. In other words, I'm going to solve for y. Y is equal to 60 minus 2x. And so I'm going to use that information in my area is equal to x times y formula. And what that does is it gives me area is equal to x times y. Well, y is 60 minus 2x. And what I have here now is a formula for area where area depends only on x. And so I can really think of area as a function of x. So area A of x is equal to 60x minus 2x squared if I distribute that x. So what we've done is we've come up with a formula to describe the area of this kennel, and that formula depends on our value for x. Okay, are there any questions about that formula? Okay. Then let's take a look at what this function looks like. If you have your calculator, please pull it out. And graph this function. You'll have y is equal to 60x minus 2x squared. Now if I do zoom standard on this, then I get something that looks like complete rubbish, and all I see is a little bit of a line right here. So in terms of trying to make sense of my graph, some things that I want to think about. What are reasonable values for x? And so when I think about this picture, I want to think about sort of the extreme possibilities. And one extreme possibility is if I push this y side of the fence flat against the wall, in which case my x value is 0. So the smallest that x could be is 0. And the largest that x could be, well, if I pull this y away, remember that I have 60 feet of fencing, and so I need to have enough fencing to take care of my top x and my bottom x. So the largest that my x value could be is 30. Because I have 60 feet of fencing and I need that top side and that bottom side. And that's sort of the extreme of let's squish the two sides of the fence together and make it really long and skinny in this direction. So looking at that, I have a little more reasonable of a picture if I change my x window from 0 to 30 and I hit graph. And it still didn't help me a lot, but what I do see is I see two parts of this curve, so I better expand my y value a little bit here. So let's go y going from 0 to, let's try 200 and see what happens. Better, but not perfect. Maybe I'll try 500 and hit graph. And so I end up with a very nice picture of a parabola. And so what that parabola is doing for us that parabola is saying, okay, I am graphing a of x is equal to 60x squared minus, what was it?
2x squared.
Oh, sorry, 2x squared?
It's 60x minus 2x squared.
Thank you. 60x minus 2x squared. Okay, so this is what we're graphing, and so on our x-axis, we are really measuring the x value on our fence. The output, the y value, the output is our area. And so whatever we choose for the x dimension, the output will be the area, and our job is to figure out when is the area the greatest. So in other words, we'd like to know for what x value is area the largest. Okay, so we want to figure out for what x value do we hit the top of this function. Okay? Now your calculator has a maximum/minimum finder on it. Okay? And so in college algebra, the next thing you would do with this question would be to go into your calculator and figure out what the x value is that corresponds to the highest point. But now we have calculus, and so we can find this through calculus. Okay? So what's happening up here at the top of this hill? What do we know about the derivative up there?
0.
Yeah, the derivative is equal to 0. And so at the top of this hill, our derivative of this function is equal to 0. So if we can figure out where the derivative of our function is equal to 0, we've solved for the x value that will give us the right dimension. Well,
You could just say since it's a simple parabola that the max would happen halfway between 0 and 30.
yes, so this is a simple parabola, and we can actually use college algebra to say, okay, this value should be 15. Okay? We're going to do some more complicated examples where that won't work for us, but on this one we can use either one, calculus or algebra. Okay, so for us, I'm going to imagine that I don't necessarily know that that x value is 15 right in the middle, but if we get an x value of 15, then we can be happy that we came up with it in two different ways. Okay, so looking at this expression here, we've got a of x is equal to 60x minus 2x squared, and we would like to find where a has a maximum value. So we'll look at a of x. A of x is equal to 60x minus 2x squared. Take its derivative. We end up with 60 minus 4x. The place where that derivative is equal to 0 is going to be where our maximum area occurs. So we'll set our derivative equal to 0 and solve for x. So we'll move the 4x over to the left side. We've got 4x equals 60. Divide by 4. And we get exactly what Will suggested. Halfway between 0 and 30 is 15. Okay, so at this point, here's what we've done. We have read the question, we've drawn a picture. From this picture, we have written down a formula for area. We started with A equals x times y, and then we used an extra relation to eventually write area as a function of one variable. Now from that, we said, okay, where is area largest? Area is going to be largest at the place where the derivative of area is equal to 0. So we take the derivative, set it equal to 0, and solve for x. Okay? So this x value is a place where a prime is equal to 0. Now, without my graph, how do I know that this is a maximum rather than a minimum? Because it would be a real bummer if I took this x value and said, okay, I'm going to make the x dimension 15, that's going to make the other x 15, and I'm going to figure out the y, and then it gives me an area, but just because I have a flat place on my function, I don't know that that flat place is necessarily a maximum. It could be a minimum. And if we're talking about something more important than a kennel, and you go back to your boss and say, here are the dimensions to give you the maximum area, and you've really given him or her the dimensions for the minimum area, then you're going to get fired pretty quick. So we want to double check to make sure that this X value will give us a maximum rather than a minimum. And one way that we can do this to verify that we found a maximum rather than a minimum is by using calculus. So we know that A, the area function, A of x, is flat at x is equal to 15, because we took that derivative, set it equal to 0, and solved for x. Let's look at A double prime. Our original function A prime is equal to 60 minus 4x. So A double prime of x is equal to negative 4. Here's our A prime. When I take its derivative, I get negative 4. When our second derivative is negative, what does that tell us about an original function? It's concave down. So A double prime being negative, this tells us that A is always concave down. So without this picture, even if I don't have this picture on my graphing calculator, my information about f prime, or A prime in this case, A prime is equal to 0 at x equals 15, A double prime is negative, tells me that my graph looks something like this. And so I'm guaranteed, because A is always concave down, and at x is equal to 15, we have a flat spot, tells me that this is definitely a maximum, and in fact an absolute maximum. So at x equals 15, we have an absolute maximum on A. Okay, so we just created a little bit of job security for ourselves. We've justified that our x value we found gives us a maximum on the area. So we have one loose end to tie up, and that loose end is to go back and reread the question at the beginning. The question says that we want to build a dog kennel attached to our house. We have 60 feet of fencing, and we want a rectangular kennel with the biggest area possible for our dog Maggie. Find the dimensions of the fence. So we have one dimension for our fence. We have the x value. And so to answer the question, the dimensions of our kennel, well, the x value is going to be 15 feet. What about the y value? Okay, so why 30? I mean, how do we know that? Okay, say it a little louder.
We have two x's, so 15 and 15 is 30.
Okay.
Take 60 minus 30, leaves you 30.
Great, so we can go back to our original picture and say, okay, I know I have 60 feet of fencing. I'm going to need 15 for each of the x sides. That takes away 30 feet and leaves me with the final value of 30 feet. Okay, so we can go back to the original question. Another way we can think about that as well is, this is erased already, but we also had a formula for y. So y was 60 minus 2x. So we can think about this either in terms of the picture, which is absolutely valid, or in terms of the algebraic equation that we came up with, which is the same idea, but conceptually, we kind of, in the algebra, we kind of forget about where all that stuff came from. So either way works, but we end up with y is equal to 60 minus 2 times 15, So our y value is 30 feet. So our kennel's dimensions are 15 by 30 feet in order to maximize the area. Okay, so what's happening on these optimization problems? When you took college algebra, you did similar problems to these, where your goal was to read the question, read the story at the beginning, come up with a function that describes the thing that we're trying to maximize, in this case, largest area. And so you came up with a formula, in this case for area, all in terms of one variable. And in college algebra, that's where you stopped. That's where you went to your graphing calculator and used that graphing calculator tool to figure out where you had a top of a hill or a bottom of the valley. What we're doing is that we're saying, instead of leaning on or using the calculator as a crutch, we are going to look at the derivatives. We're going to take the derivative, set that derivative equal to 0, find those critical numbers. And then look at our second derivative to tell us, is this a maximum or a minimum, depending on whether our function is concave down or concave up. So the calculus is in these two parts, and the setting up of the original function, this is our second go-round with that. So for those of you that didn't like it in college algebra, you get to revisit it and like it a little bit more this time. Okay, are there any questions or comments about that? Ben?
Wouldn't the biggest area be 20 feet by 20 feet by 20 feet?
That's a good question. So your thought was 20 feet by 20 feet by 20 feet, which our calculus didn't give us that as an answer. So why don't we take a look at if we...
That's 30 by 50.
So with the 20 feet by 20 feet by 20 feet, this is a terrible marker. Somebody is very angry when they teach because every single one of the markers that are in here, the little thing is pushed all the way back in. Okay, so you're 20 feet by 20 feet by 20 feet. Well, that's going to give me an area of 400 square feet. Up here, if I do 15 times 30, what do you get when you multiply that out?
Okay.
So that gives us 450 feet. Now, I think where your intuition is failing you here is that because we're using the house as one side here, that means that we don't have, your idea of a square would give us the largest area would be true if I was building the kennel out in the middle of my yard and I had to put fencing on all sides, then a 15 by 15 by 15 by 15 would be the largest area. But because we are up against the wall, that changes our dimensions. All right, other questions? Daniel?
Well, you found that 15 was a local max by looking at concavity. Would we be missing something if we just did like, we tested values under 15 and above 15 and counted those somewhat positive and negative?
So you want to test those values in F prime?
That's just like how I would.
Yes, so the two things that are sort of, there's a small subtle difference between these. And what we actually found here is that by doing that, which can work as long as you can say the function x is always increasing up to 15 and then always decreasing afterwards. So that would work. What you want to be careful of is when you have a function that looks like this, and then you find a local maximum, but it's not necessarily an absolute maximum. And what this argument is doing is you're doing a first derivative test, and I'm essentially doing a second derivative test. Both are valid. Okay. So as long as you can say f prime is always positive and then always negative after x equals 15, that's legit. This is saying f double prime is always negative, so that's another way of talking about it. Both would work. Other questions or comments? Okay, so what I'd like to do then is to give you some practice problems to work on.